Okay, let's start. So now we are doing differentiation graph, especially rational function type. Then today need to do advanced questions. So let's do past paper questions. Okay. Before that, I need to revise you something that is about second derivative test. Just write down topic second derivative test. Just write down topic second derivative test. Second derivative test. Second derivative test. Here this is important. So you consider function fx, y equal fx, then differentiate, we get dy by dx, we say f dash x, then second derivative d squared by dx square, we say f double dash x. Here this represent gradient. This represent gradient. Here by this you can find critical point. Can obtain critical point. Okay, we can obtain critical point, and also we can obtain increase in, decrease in regions. Can obtain increase in, decrease in regions. Then second derivative, here we can obtain concavity. Okay, there's two things, one is concave up, the other one is concave down. Concavity, concave up, concave down, two things. So and further, by second derivative can obtain type of critical points. This is the thing. Okay, now see this one first. So we know when we differentiate the function, we get gradient, no? We get gradient. So when f dash x greater than 0, it is increasing. Here f dash x equals 0, here gradient 0. F dash x less than 0, now it is decreasing. 3 decrease in type. 1, 2, 3. Okay. Then second one f dash x, f double dash x. F double dash x 0 point, we say point of inflections. F double dash 0 point, we call point of inflections. Here we have concave down, we have concave up. Here concave down, concave up. Concave up, concave down. Concave up and concave down. So for concave up, we say f double dash x positive. For concave down, we say f double dash x negative. Negative. This is the thing. Okay. Write down this one. Write down. By using second derivative, we analyze about concavity. By using second derivative, we analyze concavity. There are two cases. First one concave up, First one concave up, second one concave down, second one concave down. First one concave up, second one concave down. Next tarmac, by using the second derivative, 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 critical points also can be analyzed. Critical points also can be analyzed. Critical points also can be analyzed. Okay, first you write this one. First write that. Okay, further you write this one. Further you write this. Okay, now let's move a little further. This is important thing. So derivative 0 point we call critical point. No? Derivative 0 point we call critical point. Then there are two different types of critical point. One is turning, the other one is point of inflections. Turning point and point of inflection. So under point of inflection we have two again, increasing inflection, decreasing inflection. So under turning point we have two, one is maximum and the other one is minimum. Okay, so you consider function y equal fx. So differentiate. Then we get f dash x, no? dy by dx. Then f dash x 0, here to get critical points. Then further differentiate. Then we get d squared by dx square or f double dash x. So you say here critical value x equal a. Here critical value. Let a critical value x equals a. So by this one you can identify the type of critical point. So you substitute that value here, f double dash a. Here we denote d squared by dx square x equal a or f double dash a. So here we can get three things. So one is positive value, the other one is negative value, the other one is zero value. We will get three things. So here the way function differentiate, obtain first derivative. Then f dash x 0 we call critical point. Here this is critical value. So here second derivative. So you substitute that critical value to the second derivative. When you substitute critical value to first derivative, we get 0. So here second derivative, we have substituted critical value. So there will be three possibilities. One is positive, the other one is 0, the other one is negative after substituting. So if we get negative value, we say local maximum point. Local maximum point. For negative value maximum, for positive value you say local minimum point. Here point of inflection. That's how we identify critical point using second derivative. Just put that one as well. That's not necessary, but you have to remember this one. Okay, now let's move a little further. Let's move a little further. Now you consider so in a graph we have here this type of shapes. Here this type of shapes. So these are we call critical points, no? So when we sketch a tangent, so that is parallel to x-axis. Parallel to x-axis, we call critical points. So in a graph we may see this type of shapes again. Here these are called vertical asymptote, no? Vertical asymptotes. So again you may see here y-axis, here horizontal line that gonna touch some axis parallel to x at the x as x goes to infinity. X goes to infinity. This is called horizontal asymptote. Horizontal asymptote. Horizontal asymptote. Here vertical asymptote. And here this is called critical point. Here these are special points, special shapes. And further we have another one. So that is, so you consider a graph like this. This is concave down case. So now it's gonna change to concave up. So concave down change to concave up case. This point we call point of inflection again. Here concave down change to concave up case. Concave up change to concave down case. Here this is concave down to concave up change. Concave down to concave up to concave down change. So likewise here concave up to concave down change. So anyway, when you sketch tangent, here we can sketch a tangent here at this point. So this is point of inflection again. Point of inflection. Inflections. We have two types. Here vertical asymptotes, here horizontal asymptote. These are critical points. And again we have point of inflections. So when we sketching graph, we see in future this type of shapes. Also we have done this thing before. But anyway, here this type of point of inflection we identify using second derivative. Here check by second derivative. Second derivative. Okay, put that note. Here don't mislead this with this one. This also we call point of inflection. Here increasing inflection, decreasing inflection. So here the specialty concave down, then it changed to horizontal level, horizontal position, then concave up, horizontal. Here concave up, then horizontal, concave down. Then here critical point when you sketch a tangent, that is horizontal. Okay, horizontal one. Then here this one another different thing. So here concave down change to concave up. Then here that tangent not horizontal. Here tangent slant inflection. So that can be vertical one. That can be vertical or that can be slant. Here concave up change to concave down. Here slant. This is horizontal. So here derivative, first derivative 0. First derivative 0, first derivative 0 here. But here first derivative not 0. But anyway, second derivative 0 surely. Second derivative 0 here. We have to check this one. Huh? Just identify, that's enough for now. Then later we will do one by one. Okay. Now let's start doing past papers. Take your past paper set. First mark this one. First mark this one. 2003 part B. 2003 part B, we have done that before. Just mark it. 2003 part B we have done. Okay. 2015 part B, B part. 2015 part B, B part. Okay, you start it now. 2015 part B, B part. I'll give you 1-2 minutes to start it. I'll give you 1-2 minutes to start. 2015 part B, B. Okay, start it. You follow usual techniques. Follow usual technique. Function is given. Differentiate, factorize, equate to 0, identify critical point, and go likewise. Now if you have any doubt, do with me. If you have any doubt, do with me. So here the function fx equal 2x squared plus 1 x minus 1 squared. Here this is the one given. We have to sketch the graph. Check this one please. We have to sketch the graph. So when you sketch in a graph, definitely you have to differentiate that function once. Okay? You have to differentiate once first. Don't go to second derivative. So if second derivative given, then only you take that. Okay? If second derivative given, then only you take that. Otherwise you have to differentiate only once. Okay. Now here by this function we can identify vertical asymptotes, horizontal asymptote, x-intercept and y-intercept. By the function we can identify that. So here the way, let x equal 0, then you find corresponding y value. This is y, no? This is y. When x 0, here y value 1 divided by minus 1 square, we get 1. This is we call y-intercept. Y-intercept. Now do with me. Let y 0, then 0, 2x square plus 1, x minus 1 square. Then when you cross multiply, this will disappear. Then 2x square plus 1, 0. No? Then 2x square plus 1, x square equal minus half. Then we don't have any real value. No? We don't have any real value. That means no x-intercept. No x-intercepts. Here x0 take y values. When y0 take x values. Here no real values. No? Then you say no x-intercept. No x-intercepts. Then here x-intercept, here y-intercept. Then third you can find denominator zeros. By the denominator zeros you can identify vertical asymptote. Then denominator zeros. Here x minus 1 square 0, we get x equal 1. We say vertical asymptote. Vertical asymptote. Do with me, yeah? These are the special points. Denominator zeros, we get vertical asymptote. And when we get vertical asymptote, we have to check here left hand, right hand tendencies. X goes to 1 plus side, x goes to 1 minus side, y tendency. X goes to 1 plus side, we always get positive values for infinities. We always get infinities. Then here 1 plus, here infinity, no? Here put 1.1 here. 1.1, we get plus infinity. So 1 minus mean you have to substitute 0.9, some value less than 1. Here we put 0.9 here, then again we get positive value. Then both are positive infinities. Positive infinities. Then thereafter you check horizontal asymptote. So by function we can find them, okay? Then third one, horizontal asymptote. Horizontal asymptote. So here the procedure, here this function, you arrange this function, take maximum power term outside, here take again x square outside, then cancel this x square, then as x goes to plus or minus infinity, y tendency, as x goes to plus or minus infinity, here 0, we get answer 2 divided by 1, 2. Then y equal 2 we call horizontal asymptote. Horizontal asymptote. Horizontal asymptote. So that's the thing we can find by the function. So that's the thing we can find by the function. Then you move to differentiation part. You find f dash x. F dash x. Do up to that. If you have any doubt, do with me. Others do alone. Do up to that. Okay. Now you differentiate this. Rational type, no? Then denominator is square. Denominator times derivative of numerator minus numerator times derivative of denominator. So you have to find derivative. So we have rational type. Here take this. Then denominator is square. Denominator times derivative of numerator minus numerator times derivative of denominator. So when you get in derivative, we have to differentiate. We have to differentiate first. Then we have to factorize. No, we have to factorize. Then factorize this. Before that, you simplify. X minus 1 to the power 4. Here by this, we have common 2 and we have common x minus 1. Take it outside. Don't go to expansion. Just take factorization. Then here 2 x minus 1 inside the bracket. Then further we have x. Here 2x squared minus 1. Now simplify 2x square, you can cancel 2 into x minus 1. Here minus 2x minus 1. Then take minus outside. X minus 1 to the power 3. You cancel this one. We can cancel one factor. Minus 2 times 2x plus 1 cube. Here the derivative now. So by this one we can do many things. By that one we can do many things. So this is very important. With the function we can find x-intercept, y-intercept. And with the function we can find whether we have vertical asymptote or not. We can check that. And with the function again we can identify horizontal asymptote. Not all functions has vertical asymptote. Not all function has horizontal asymptote. We have to check it. Okay. Now here differentiate by this derivative. We can identify critical points. Then to identify critical points, critical values, take f dash x 0, take f dash x 0. Now here minus 2, 2x plus 1 of x minus 1 cube, 0. Now we can get one value here, that is x equals minus half. We get x equal minus half. We call this is critical value. Critical value. Okay. Then you find critical value. Thereafter you find critical point. Here when x equal minus half, you find y value. Take original function, substitute minus half. 2 into minus half square plus 1 minus half minus 1 to the power 2. Here 2 over 4 plus 1, here 9 over 4. Simplify 6 over 9, 3 over 2. Therefore, minus half, 3 over 2 you say critical point. You say that is critical point. You differentiate the function, thereafter factorize, equate to 0, thereafter find critical value. That critical value substitute the function. Continue. Now you check dy over dx sine, or otherwise f dash x sine. F dash x sine. Now when you check in the sign, when you check in sign, you have to think about f dash x, no? So here sign can change at x equals 1 by this factor, and again sign can change by this factor. Okay, then you take critical value and as well as vertical asymptote. These two we need to consider, vertical asymptote and critical value, both we need to consider, because here this is f dash x, then according with this factor sign can change, according with this factor again sign can change, no? Therefore here take minus half, and here plus 1, 1. Here it is. Okay. Now carefully see here f dash x. Carefully see this one. Here this factor leading term positive. Here this factor leading term positive. So usually for linear factors, sign variation, right hand corner one positive, then negative, positive, it change. That is usual thing, general thing. Right hand corner one plus, then minus, then plus, it goes like that. Here odd power, then definitely sign will change. Here odd power, sign will change. But again we have outside minus. Then usual one right hand corner plus, minus, plus. But here we have minus outside. Therefore again we have to reverse the sign. Therefore previous case plus, minus, plus, now you have to reverse the sign. Here you put minus, plus, minus. No need to substitute values. You can just write it, okay? So anyway, now here critical value, minus half, no? This is critical value. Then here critical point. This point critical. Then minus to plus variation. Minus to plus variation, we know that is minimum shape, no? Here critical point, but here vertical asymptote, x equal 1 vertical asymptote. Here critical point, but x equal 1 vertical asymptote. Don't mislead plus to minus like maximum, don't mislead that one. Here minus to plus critical point, then it is minimum. Here plus gradient, here this way acute angle touch, then you sketch acute angle touch like this. Left side, right side negative, then obtuse angle touch. Negative means obtuse angle touch. Here acute angle touch, obtuse angle touch. Now here vertical asymptote, here critical point. Now already we have identified x-intercept, y-intercept, and vertical asymptote, horizontal asymptote, critical point, and we have identified the type of the critical point. Then we can sketch the function. Now here the procedure. Now start sketching. Here x-axis, this is y-axis. If you have any doubt, just say first. X-axis, y-axis. So when you sketch in, you better to get vertical asymptote first. X equal 1. Here's simplification 2 over 3. Yeah? 2 over 3. Not 3 over 2, 2 over 3. Okay. Now you're sketching the function, you first take vertical asymptote. Vertical asymptote at x equal 1, you mark it, dotted line. It is 1. Vertical line, vertical dotted line. Then you go to critical point. Here mark this point. That is minus half. Minus half 2 over 3. So minus half somewhere here, no? Minus half 2 over 3. Here 2/3 minus half. Here critical point. We have identified that is minimum shape. You sketch minimum shape here. At this point, you sketch minimum. Okay. Now here, one right hand touch here this way. You touch this way. Here the graph. Then here y-intercept, we have done that before. Y-intercept is 1. Here y-intercept is 1. Here y-intercept 1. Okay. Now right hand touch here, it's like this. It's like this. Now then go to horizontal asymptote. Here it is. Horizontal asymptote y equal 2. Then you have to sketch horizontal 2 here. Then here 1, you sketch horizontal 2 line. Here this is 2. Now you have to touch that one when x goes to infinity. You touch this side. Then here it is concave up case, then you have to touch it. Then you have to change that into concave down. Then here concave up, need to change concave down. Here there will be some point here, second derivative 0 point. But here second derivative analysis is not given. Therefore no need to worry about that. You just sketch that function this way. Here minimum concave up, concave down. This is our final graph. Final graph is that. Okay, complete it. Complete it. So when you go left to right, here decreasing, here decreasing, then start increasing. Okay. Then minus infinity to minus half, decrease in function. Then half to 1, it is increasing region. Then 1 to infinity, again going to decreasing. Then decrease in region, minus infinity to minus half and 1 to plus infinity. Increase in region, minus half to 1. Increase in region, minus half to 1. So this is our final graph. Complete. Okay. Now let's do another question. Come to 2016 part B, A part. 2016 part B, A part. First you start. So anyway, the procedure, we need function. So in that function we have factor format. Here already factorized now. Then if the function given, you check denominator factors and numerator factors first. Thereafter, this is another format. We have to take maximum term outside. We get that one to analyze horizontal asymptote. So when you factorize numerator and denominator, then we can find denominator zeros and horizontal asymptote, and these things we can find. Thereafter, you differentiate and find derivative, factorize it. Then dy by dx 0 point obtain. Then that value substitute to the function. Then you get critical point. Then so on you go along the path. Okay, start now. 2016. Start. Part B, A part. Part B, A part. If you have doubt, do with me. Others do alone. So here the function fx given x minus 3 square over x square minus 1. X square minus 1. So in function, we better to get three different formats. So one is factor form. Then you better to factorize this. X minus 3 square, it is already factorize now, then denominator factors x minus 1, x plus 1. We need this because we need denominator zeros. And there's another format. You better to get maximum power term outside, that is x square, 3 over x squared, here take x squared, 1 minus 1 over x squared. Then cancel. Here we need this one to find horizontal asymptote, terminal tendencies. So we need different three formats. So by this one, you find, let x equal 0, you find y-intercept, x0 y value, minus 3 square, over minus 1, we get minus 9. Na? When x0, here 0, minus 3 square 9, here this is equal y-intercept. Let y equal 0, now you go to here factor format this, y equals 0, then x minus 3 squared over x square minus 1 0, no? Then we get x equal 3. Here we say x-intercept, x-intercept. Then check denominator zeros. Denominator zeros. Then x minus 1, x plus 1 0. Then we have x equal minus 1, x equal plus 1. We have 2. We call vertical asymptote. Vertical asymptote. So then you have to check tendencies, minus 1 plus, minus 1 minus, y variation. You have to check this. Then x goes to 1 plus, x goes to 1 minus, y variation you have to check. All cases they are infinities. All cases they are infinity. Then 1 plus mean, take 1.1 and substitute here. Take 1.1 and substitute here. This factor form needed to check this vertical asymptote. 1.1 positive, positive. Here always substitute positive, we get positive answer, plus infinity. 1 minus means substitute 0.9 here. Here negative, positive, positive. Then we get negative answer. Here minus 1 minus mean, take 1 point minus 1.1, negative, negative, positive. Then finally it is positive. Minus 1 plus mean, take minus 0.9, then minus 0.9, here positive, negative, positive. We get negative answer. Those are vertical asymptote. So later you can miss this one because by derivative sign we can check it again. Then you consider here this format, horizontal asymptote. Asymptote or terminal tendencies. Here by terminal tendencies. Then as x goes to plus infinity, plus or minus both case, here 0, 0, we get answer 1. Then y tendency to 1. This is horizontal asymptote. Y equal 1, horizontal asymptote. Horizontal asymptote. Then we have identified vertical asymptote. There are two. We have identified horizontal asymptote. We have identified x-intercept. We have identified y-intercept. Thereafter, further we need to differentiate the function. Then you differentiate this function. Find f dash x. Then we have denominator, then denominator square, denominator times derivative of numerator, 3 into x minus 2 minus numerator times derivative of denominator. Here it is. Okay. Now you need to simplify. Here factorize denominator x minus 1, x plus 1, whole thing square. Then for this case we have to factorize x minus 3 common, no? Here something wrong, no? X square denominator times derivative of numerator 2 times x minus 3, okay, minus numerator times derivative of denominator. Now it is okay. Now here 2 times x minus 3 common, take it outside, then x square minus 1, 2 times x minus 3, then here x square plus 3x, then cancel 2 times x minus 3, 3x minus 1, x minus 1 square, x plus 1 square. Here the derivative now. Now that derivative not given, then we have to do that one. No, that is given, no? 2 times x minus 3, 3x minus 1, x square minus 1 square. That is given. So here the derivative. So you differentiate first, thereafter take common terms outside. Then likewise you go factorization. Don't go to expansion, just think like multiples. Then to find critical values, solve f dash x 0. So 2 times x minus 3, 3x minus 1 over x minus 1, x plus 1 square. Now we get two critical values, x equal 3 and x equal 1/3. These are we call critical values. We call critical values. Continue up to that. We call critical values. So here procedure same procedure, only function will change. Only function will change, the procedure same, then you can easily do this section if you practice this one. Okay. Now with the derivative, we can identify critical points. Here critical value, no? Then you identify critical point when x equal 3. When x equal 1/3, we have 2, no? We have two critical points. Then you can find x value, y value by using the function, no? By using the function. Substitute x equal 3. So when you substitute x equal 3, corresponding y value, 3 minus 3 square, 3 square minus 1, we get answer 0. Then critical point 3, 0. So similarly, when x equal 1/3, again you substitute here, substitute 1/3 here. Then corresponding y value, 1/3 minus 3 square, 1/3 square minus 1. Here 9, 8, 64 over 8 minus, we get minus 8. Then 1/3 comma minus 8, another critical point. Critical point. Here 9, 8 square 64 divided by minus 8. We have two critical points. Two critical points. Continue up to that. Continue. Now you check dy by dx sign or f dash x sign. So when you check in the sign, you have to think about denominator zeros and critical values both. So you can identify that from here. So here 3, 1/3, 1 minus 1. 3, 1/3, 1 minus 1. So here better to mark that on the number line. Here 3, no? Then 1/3 somewhere here. Then 1 somewhere here. Minus 1 somewhere here. Then you have to think the region. Then start with minus 1. Then you go to 1/3. Then you go to 1. Then you go to 3. Then likewise you have to split it. Carefully see how to check signs. Now here leading term positive. Then here square means sign won't change, no? For even power, sign won't change. At 1 and at minus 1, sign won't change. Check this one clearly. Even power, then at x equal 1 and minus 1, sign won't change. So only sign change at 3 and 1/3. Here 1/3 here, so sign change here and sign change here. Okay. Then if leading term positive, surely right hand corner one positive. Yes, right hand corner one positive, then you change sign, minus, then here sign won't change, minus, then you change sign again, plus, then sign won't change. Right hand corner one plus, then change sign here, sign won't change, sign change, sign won't change, no? So here this one sign change. Then here we have two critical values now, 3 and 1/3. Here critical point, plus to minus, you identify maximum, minus to plus, you identify minimum. These are critical points. Critical points. So here minus touch means obtuse angle, gradient minus, obtuse angle touch. Here we sketch this way, here touch, okay, minus touch. Here plus touch means acute angle touch. Here. Likewise, we can sketch touch. Now we have two vertical asymptote, two critical points. Therefore, here 1/3 8, that is local maximum. Here local maximum. Here 3 0, that is local minimum. Local minimum, local maximum. We have two things. Now already we know x-intercept, y-intercept, vertical asymptote, horizontal asymptote, critical points, all are known. We have identified type of critical points. Type of critical points again we know. Okay, now we can sketch the graph. Complete up to that. Now sketch the graph. So you start with denominator zeros first. Let's sketch. Here y-axis, x-axis, label them. Then we have two vertical asymptote, 1 and minus 1. Here 1 and minus 1. These are vertical asymptote. And then go to critical points, 3 0. Here 3 0, 1, 2, 3. 3 0. So 3 0 local minimum, sketch minimum shape. Then 1/3 minus 8. Here 1/3 somewhere here. Minus 8. I'll take here. That is local maximum. Local maximum. Now, when x goes to 1 plus side, here 1 plus side, here we have to touch this way, then match this graph. 1 minus side, here minus infinity, then you touch this axis, match this shape, and again you match this one. So here again y-intercept, we got that now, y-intercept minus 9, you mark it, minus 9. Here 3. Then minus 1, minus side plus infinity. Then you go to horizontal asymptote. Here y equal 1, horizontal asymptote. Then y equal 1, you sketch this way. Sketch dotted line, that is horizontal asymptote. So when x goes to plus infinity, y goes to plus. Here you clearly show this shape change. Here concave up has changed to concave down. Then there will be point of inflection here. Here concave up, then it changed to concave down. When x goes to minus infinity, that goes to 0. Here it is. Here this point, second derivative 0 point. Second derivative 0 point, but here second derivative not given. Second derivative not given, then no worries about getting second derivative test. That is 2016, no? 2016. Complete it. Complete. Okay. Now check this one. Here x goes to plus infinity. X goes to plus infinity, y goes to 1. So horizontal asymptote mean we have to touch that line. Vertical asymptote mean again we have to touch. Don't cut. Huh? So here when x goes to plus infinity, y must go to 1. So if you sketch this way, it cut y equal 1. Then that is not the way. We need to touch it. Therefore, here when x goes to plus infinity, you need to change this variation. Then only we can touch it. Otherwise, it will cut. Then x infinity, it touch. So when x goes to 1 plus side, we have to touch it. Okay? Don't sketch like cut. It is wrong. Don't cut it. So when it touch, stop sketching. So when it's touch, stop sketching. Okay? Okay. Now let's do another one. Okay, you come to 2017 question. 2017 A-level question. Start it. 2017. Part B. A part. ඒ ටියුට් එකේ part A part B කියලා දාලා නැහැ. ඒක අර A part එකේ තියෙන question එක ගන්න graph එක. 2017 fx equal x square over x minus 1 x minus 2. Do this. X square over x minus 1 x minus 2. Do it. Start. Carefully. Your function given when x0, y value 0, y-intercept. When y0 corresponding x value 0, x-intercept. Denominator zeros, x equal 1, x equal 2, vertical asymptote. So you better check tendencies x goes to 1 plus, x goes to 1 minus, y variation. And x goes to 2 plus, x goes to 2 minus, y variation. This is not compulsory, yeah? But better to get it. Then all are infinities. 2 plus mean 2.1 positive. 2 minus mean take 1.9 positive, negative, positive, then negative. Then 1 plus mean take 1.1 plus, minus, plus. Then minus, 1 minus mean take 0.9 minus, minus, plus. You get plus. Then you check y equal 1 over here x square, no? Take x square outside, 1 over x, 1 minus 2 over x. Then cancel. Then x goes to plus or minus infinity, y tendency here 0, 0, 1. Then y equal 1, horizontal asymptote. Horizontal asymptote. Then 2 vertical asymptote. Y-intercept, x-intercept, that means passes through the origin. Then you differentiate, find f dash x. Denominator square, denominator times derivative of numerator, numerator times derivative of denominator. You have to practice just rational type derivative with function of a function. Now simplify. Here x minus 1 square, x minus 2 square, get common terms outside. Here x common, take it outside, then expand this. 2x square minus 6x plus 4 minus here 2x square minus 3x plus 3x. Now simplify. X minus 3x plus 4. So x minus 1 square, x minus 2 square. Take, so we have to show something, no? We have to show 4 minus 3x. Now already there. Here it is. Now to find critical values, take f dash x 0. Then f dash x 0, we get x equals 0 and x equals 4/3. Here critical values. So numerator zeros of the derivative will be critical values. No? Here critical values. Then by that one you can find critical points. By that one you find critical points. Continue. Then find critical points. When x equal 0, y value 0, when x equal 4/3, corresponding y value substitute, 4/3 is substitute the function, 4/3 minus 1, 4/3 minus 2. Simplify. Here 16, 1, 2. We get 8. Minus 8. Here 3 square cancel, 4 square 16, 4 minus 3 1, 4 minus 6 minus 2, minus 8. Therefore, critical point 0, 0, 1, the other one 4/3, comma minus 8. Here these two critical points. Critical points. Then we have to identify the point by checking f dash x sign. We have to check the sign, no? So the sign check. Here you take this. You have to check denominator zeros, numerator zeros. 1, 2, 0, 4/3. 1, 2, 0, 4/3. Then start with 0 first. 0, 0. Then 1, 1, 1. Then 4/3. 4/3, 4/3, then 2. Greater than 2, in between 4/3 to 2, in between 1 to 4/3, in between 0 to 1, in less than 0. So you can put sign directly. Here sign won't change at 1 and 2 because even powers. Then at 1 and 2 sign won't change. But sign change at 0 and 4/3. Here 1 is here. And 4/3 here. Sign change that point. Then when you check leading term, here leading coefficient negative. Here x square negative, no? Then right hand corner one usually positive, but here negative, therefore right hand corner, now you say negative. Usually positive, but we have to change it now. Now you change the sign, plus, no change, plus, change the sign, minus. Here no change, minus. Okay. Here critical values, here one critical point here. Then minus to plus variation minimum, plus to minus variation maximum. Then 0, 0 local minimum, here local maximum. Then plus touch, here plus touch, acute angle touch. Here minus touch, obtuse angle touch. Here it is now. Now we know everything. Now we can sketch the graph. Do up to that. Okay, now let's sketch. So when we sketch in the graph, we better to start with vertical asymptote. Here y-axis, here x-axis. So one vertical asymptote is 1, another vertical asymptote is 2. Mark clearly by the dotted line. Then you go to critical points. 0, 0, mark it. We know that is local minimum. Better to show this. Then 4/3 somewhere here. 4/3 minus 8. It is local maximum. Here 4/3. Okay. Then 2 minus side, it touch vertical asymptote. Here it touch vertical asymptote. Then 2 plus side, plus infinity. It touch like this. 1 minus side. Here touch like this. Now you sketch horizontal asymptote. It is y equal 1. Horizontal asymptote y equal 1. Then mark it. Here horizontal asymptote So as x goes to plus infinity, y need to touch. So you mesh this graph, you have to touch it. When x goes to minus infinity, again you have to touch it. Now it is like this. Here concave up change to concave down. Concave up change to concave down. Here second derivative 0 position. So here it has only one x-intercept and y-intercept that happened at the origin. That happened at the origin. Here this case also second derivative not given. Second derivative not given. Therefore don't worry about second derivative test. But from 2019 in some years 2019 second derivative given. In such case we have to check second derivative test. We have to check second derivative test. Okay. Complete. Here all procedures are same, only function will be changed. Then easily you can identify the question. You have to think on little thing. Then try 2021. Before that we have another one thing. No? So we have to solve the inequality. No? We have solved that inequality, that is there's inequality given x squared over x minus 1 x minus 2 less than or equal 0 case. Yeah, this means y less than or equal 0. No? This is our function y. No? So y less than or equal. Here for this region, y negative, all the other cases y positive, here again y 0 position, then solution x equals 0, x in between 1 to 2, here the solution set, okay, y 0 here only, then y negative region, 1 to 2 region y negative, okay. (2021). Let's do that. 2021. Okay, start. 2021. Part B, A part. Fx given 4x plus 1 x into x minus 2. 4x plus 1 x into x minus 2. First we have to find derivative, no? We have to find derivative first, and finally we have to sketch it, no? Then according to given flow you do it. F dash x into x minus 2 denominator square, denominator times derivative of numerator minus numerator times derivative of denominator. Now simplify x square, x minus 2 square, here 4x square minus 8x, 2x minus 2, minus 8x square, 2x, 8x, 6x, plus 6x, plus 2. Then minus 4x square minus 2x plus 2. Then take minus 2 outside. Then further factorize. Two x minus 1, x plus 1, x square, x minus 2 square, 2x minus 1, x plus 1, okay, no? 2x square plus, okay, 2x square plus x minus 1. Now it is okay. That is the derivative. We have to find that. Hence we have to find increase in decrease in intervals. Now to find critical values, take f dash x 0. Then x equals half and minus 1 are the critical values. Then check f dash x sign. To find increase in decreasing region, you have to get these. Now you have to think about critical values and denominator zeros. So x equal minus 1, critical value minus 1, then 0, then half, then 2. Then find sign of dy over dx. You have to check the sign. Then here dy over dx, we know even power no change. So at half and minus 1 it change. Here minus 1 and half it will change the sign. Then usually right hand corner one positive, but here negative, no? Negative, then change positive, no change negative, no change, change. Then critical point, local minimum. Then here touch, positive touch, maximum, negative touch. Here this is increase in region, we have to identify increasing region. Here increasing, here increasing, here increasing, always increasing, no? Then here decreasing, here decreasing. Then increasing regions minus infinity to half increasing regions. But we have to split it. Minus infinity to -1, -1 to 0, 0 to half. Then decreasing region half to 2, greater than 2. Then we identify critical values. When x equal half, check y value. Substitute half here. 4 times half plus 1 over half, half minus 2. Simplify. Here 2, 3, 12, 3, minus 4, minus 4. Here 2, 1, 3. Here minus 3, cancel with that one, minus 1, then minus 4. Therefore, critical point half, minus 4. Then similarly, x equal minus 1, corresponding y value. Put it here. 4 into minus 1 plus 1, minus 1, minus 1, minus 2. Simplify. Minus 4, minus 3, minus 1. Here critical points. These are critical points. So here minus 1 case local minimum, half case local maximum. Now we can sketch, but we have to find vertical asymptote, horizontal asymptote, x and y intercept. No? Okay. Now fx for x plus 1, x into x minus 2, when x equals 0, y value, no real value, no? Therefore, no x-intercept. When y equals 0, x value minus 1/4, here y, no y-intercept. Here x-intercept. Denominator zeros. X equal 0, x equal to vertical asymptote. X goes to 0 plus, x goes to 0 minus, y variation. They are infinities. 0 plus 0.1. Positive, here 0.1, positive, negative, positive. Negative answer. Then 0 minus mean minus 0.1, negative, negative, positive. Then x goes to 2 plus, x goes to 2 minus, y variation. That is always infinities. 2.1 positive, positive, positive. 1.9 positive, positive, negative. Then 4x plus 1, x into x minus 2. Now divide by x. Now we know here, as x goes to plus or minus infinity, y tendency towards 0. So we know how to get them directly. We have identified last day. So for proper rational functions, here power 1, here power 2, no, it is proper. For proper rational function, as x goes to plus or minus infinity, y tendency to 0 always. Y tendency always to 0. Okay. Now we know critical points, we have identified that, and we know x, y intercepts and horizontal vertical asymptotes. Then we can easily sketch it. Now when sketching, you sketch y axis, x axis. Now vertical asymptote, there are two, x equals 0, x equal 2, here one vertical asymptote, then another vertical asymptote. Then you take critical points, half minus 4. Here 1 is here, half is here. Half minus 4, mark it. Then that point is half, that is maximum point. Here maximum point. Then here minus 1, minus 1. Here minus 1 somewhere here. It is maximum point. Now check x goes to plus in 0 plus, 0 plus, minus infinity. You touch this axis. Careful doing. 0 minus, plus infinity. That's why I told you here we don't have any y-intercept. It touch axis. Then 2 minus, minus infinity. Touch this axis. Touch that axis. Then 2 plus, plus infinity. Then here x goes to plus or minus infinity, y tendency to 0. Here the graph now. So here we have touched 0. So there's second derivative 0 position here. So anyway, this is the graph. That's the graph. Okay. Complete it. Complete. Okay, now there's another thing to discuss. Find all real values of x satisfying the inequality fx plus modulus fx greater than 0. Check this one clearly. Here this is fx graph, that is fx, okay. See this one clearly. Here white color one fx, white color one fx graph. Now you sketch modulus fx. So we have property when sketching modulus function, no? When getting modulus, we have to reverse negative values positive, no? Not for positive values, but negative value we have to reverse. Here negative values, no? Here negative values, you reverse it. Here orange color one, modulus function. So for this part it won't change, then it coincident. Then here negative one, you again sketch positive. Here it goes to 4. Here orange color one, here this graph for modulus f. Here this won't change, it is positive, no? It coincident. Then modulus fx. Orange color one, modulus fx. Then we have to think about addition. Fx plus modulus fx, that is given greater than 0. See clearly, yeah? See clearly. Now you have to add white color graph and orange color graph. So when you add these two, it will get 0, no? Here positive, negative, only sign change. So then from here to here, the addition yellow color one, this is yellow color one, no? Here, then by the here orange color one, white color one addition, it double, no? Then it change, turn, it goes somewhat upward. So when you add these two, positive, negative, then 0. Then when you add these two, it get double. It get double. Okay. Then finally, positive region, here 0, don't worry about that. Here, x-intercept, previously we obtained, no? Minus 1/4. Then here, minus 1/4 to 0. It satisfies this inequality. Minus 1/4 to 0, it satisfies the inequality. And again, greater than 0, greater than 2, again that satisfies the inequality. Union x greater than 2. Here the inequality, okay? So white color one, our original fx graph. Then modulus mean negative values you need to change to positive. That is modulus graph. Then addition, yellow color one, addition. Then yellow color one we have to check, that must be positive. Then zeros forget. Then minus 1/4 to 0, positive. And here again 1, 0 to 2, again 0, greater than 2, positive. Therefore, here the corresponding region. Complete. Okay, now let's have a small interval.